I'd say at the very least, I feel comfortable getting rid of a and b. If you plug in different values for x, you'll notice that, you're going to get different answers. And obviously a and b are just a single number. The way I'd solve this one is I'd plug in a value for x. And in general, when you do that, x cannot equal 0, 1, or 2. This is a strategy that we'll use a lot, plugging in values like this. And just, keep in mind, never use 0, 1, or 2. You can, however, use 3. So what I would do here is I'd plug in x equals 3 into this equation, and I would get, let me use a different color here. So I would get 5 times 3, which is 15, minus 2, over 3 plus 3, which is 13 over 6. The right answer between A, B, C, and D, if you plug in, x equals 3, you'll get 13 over 6. So plug it in over here, and you get 5 minus 2 over 6. We'll rewrite that 5 as 30 over 6. Same thing, right? Just common denominator. Well, shoot, that's, oh, no, I can do math, I promise. That'd be 28 over 6. That's not right, so we'll go ahead and get rid of that answer choice. You can try out A and B if you want. I'll let you know right now they're not going to work. Then D's our only answer left, but let's just check it really quickly. Again, I'm going to put it in terms of 30 over 6 instead of 5. 30 over 6 minus 17 over x plus 3 is 6. And guess what? That's 13 over 6. Boom, boom. D is going to be our right answer. Plug it in and solve. And that's really all it is. Now, that's not like what they're looking for, but that's what you can do whenever they ask you, or most of the times when the SAT asks you for an equivalent form. The other way of doing this that I think is like worth exploring briefly, just as a reminder, is this is division between two polynomials. So you might remember having done like long division previously. I think it'd be x plus 3 into 5x minus 2 is how you'd write that. And you might remember like, doing this in algebra 2. Seeing how many times x plus 3 goes into 5x minus 2. There's a bunch of rules for it. Kind of, silly. You can also do synthetic division. If you remember that, you'd put a negative 3 up here, and then you'd do this whole thing. You'd write out like 5 and then negative 2. But, really what I would do actually is, I'd point out that each of the answers have 5 in it. So really the thing that you're looking for is the remainder. Notice how over x plus 3, over x plus 3, over x plus 3. Technically, we can solve this just by looking at the remainder. So I'll use this opportunity to share with you the remainder theorem. Give me a moment just to write that out. The remainder theorem will show up in other ways, in other forms across this test. And if you don't remember it, I want to use this opportunity to review it. What the remainder theorem states is, if you have a division problem like this, but specifically in the form of a polynomial divided by x minus some number a, that if you plug a into the original equation, if you plug a into the original equation, that will give you the remainder of this operation of the division. So my f of x here would be 5x minus 2. And again, what the remainder theorem tells me is that if I plug in, it would be negative 3 if I plug in negative 3, because x minus a equals x plus 3, right? That's our underside. Get rid of the x's, negative a equals 3, therefore a equals negative 3. So if I plug in negative 3 for x, then what I get out here is negative 15 minus 2, negative 17, and guess what? Boom. Well, it's a minus there, so I'll include that. Negative 17. There are other remainder theorem problems that I think are a better example of like the remainder theorem, but while we're here, I just want to go over this and remind you. It's a very specific thing, and you'll notice it when, whenever they test you on it. It'll be like kind of obvious. I'll see if I can pull up an example really quickly. I might not have one saved right now though. Oh, here it is actually. Cool, my organization's gotten a lot better. So let me just make that a little bit better visible. So this one's a lot more clear. It's like a lot more obvious, I think, that they're asking about the remainder theorem because they explicitly say, like the remainder when p of x is divided by x minus 3. Again, notice that it has that form. Let me bring all this back up. Remainder theorem, the whole point, let me get rid of all these extra things. The whole point of remainder theorem is that if you have that division, oh, actually, no, I need to get rid of all of that. Never mind, sorry. But the whole point of remainder theorem is that if you have, a polynomial p of x, so p of x divided by x minus a, you can, again, plug in a into the p equation, p of a, and that will equal your remainder. So they say the value of p of 3 is negative 2. Well, what that means is, again, that means that our a value would be 3, and the remainder would be negative 2. So that means that it's whatever p of x is divided by x minus 3. Whenever we do that operation, our remainder is negative 2. And that's exactly what D is saying here as well. The remainder when p of x divided by x minus 3 is negative 2. They're saying something similar right here when they say it is a factor. Obviously, none of these numbers make sense, x minus 2, x minus 5, or an x plus 2. But when they say it's a factor, they're saying the same thing. They're saying the remainder when p of x is divided by whatever is 0. That's what, a factor is, right? If you have a remainder of 0, it's a factor. So it's still like, those three look very different, and you might think like, oh, well, cool. Am I just going to go for, the odd one out every time? Not necessarily. It's just that, they're trying to throw you off there. They have all sorts of tricks to throw at you. But that's another like very straightforward example of the remainder theorem that you might see on the SAT, as opposed to the one that we just solved, which, as I mentioned, could also be solved just by plugging stuff in.